So I was trying to think how I could explain the next thing without using like a chicken analogy, but I can't, so I'm just going to go to this chicken analogy, okay? You have a chicken, which I will now attempt to draw. So we'll make it sort of a biomedical engineering. Oh my God, okay. Okay, here we go. There's a chicken. And there is a bone inside the chicken, and you work in a laboratory that is very interested to understand how strains develop on bones. And in fact, there are laboratories that do this, right? They're interested in bone biomechanics, and as you've learned, strain is a very important quantity to learn, right? And so they would want to measure, for example, as this chicken walks, as it's exposed to some sort of stress, right, an accident, what is the strain on this bone? Now, the way you would do that, right, again, this is not a hypothetical example, there are labs that do that, is you would need to use a strain gauge, right? That's the sensor you want to measure. But I want you to notice that when you use a strain gauge, you're going to have to, I'll draw this as a tube here, you're going to have to attach it to the bone, right? You can't have it floating on the surface of the chicken or even insert it into the chicken and have it floating around. You need it attached to the bone so that when the bone bends, the strain gauge bends with it, right? And so you would have to do a little operation on this chicken, implant the strain gauge, seal it up, and have two wires running out of the chicken, and here you have a resistance that is a function, or is a function of the bone strain. Okay. So far, so good for this hypothetical example, right? And then you would connect this to a voltage divider. Why not? You're doing this experiment, right? And sure enough, you discover that whenever the chicken walks, there's a little bit of an increase in strain, as in there's a slight bend of its bones, right? Every time it walks, right? Strain, strain, strain. And then at some point, right, like chickens will do this, it just stops walking. And then you notice that the strain, right, doesn't move. So the chicken is just standing there, and there is no change in the strain because it's not moving. And you're sitting there and you're watching it, the chicken's looking at you, you're looking at the chicken, right? And all of a sudden you notice that the strain is starting to go up a little bit. It's moving up very slowly. And you're like, that's interesting because, you know, chicken's not moving, but maybe something is happening, right? So you're recording it, right? And at the same time, in this hypothetical example, you start to get very warm because it's a hot day. So you're getting hotter and hotter, all right? All right, as you get hotter and hotter, well, let's wait for that to pass. All right, so this is the most awkward example, but anyways, you're watching the chicken, it's watching you, the room's getting hotter and hotter, and you notice that as the room is getting hotter and hotter, you keep measuring an increase in strain and an increase in strain. Eventually, it gets to this very weird, spectacular value that shouldn't even happen, right? Then after a while, someone opens the window and the room gets cold again. Chicken's still looking at you, you're still looking at the chicken, and then all of a sudden you'll notice that the strain goes all the way back down again. All right? Very awkward experiment, all right? Now, you could interpret this in a variety of different ways. You could say that as the room gets hot, something happens to the chicken and something happens to its bones, right? But in fact, that's not what happened. What in fact happened, right, in this strange experiment, is that the temperature changed. And the temperature change changed the resistance. You're going to say, well, hold on, Professor Bikson. I didn't put in a resistive temperature sensor, right? very intentionally, I went to Amazon and I purchased a strain gauge sensor, and that's exactly what I put in here, right? I even have came in a box. It's a strain gauge sensor. I did not buy a temperature sensor, right? So what? Why would you think that just because you bought a resistor whose resistance changes with stretching, its resistance would also not change with temperature? Because we know that resistors have a resistance that changes with temperature, right? Why would the one you bought not work that way? They all do, well, some of them do that anyways. In fact, what you have, to put it here, is you have a resistance of your sensor. This is this of your, let's call it resistor of your sensor, which is proportional, right, by some, let's say, by the gauge factor, to, and I'm going to write here, strain, plus another factor, and I'm going to write here temperature, right? And for convenience, I've switched away from proportional changes. You have a resistor, and the resistor is sensitive to two things. I'm going to call this thing here the signal. And I'm going to call this thing here, the temperature, the noise. Okay, there's a lot of busy stuff here. I think this is the first time maybe, or one of the first times in the course from explicitly discussing something called signal and something called noise. Right? The hard part about biomedical instrumentation, the thing that makes you $1 billion as an inventor, right, or the best R&D engineer at company X, is dealing with signal and noise. Because the signal part is actually pretty simple. The signal part is get a sensor that's sensitive to your measurand and put it in a voltage divider. That's it, right? If it was so simple, but it's not. The problem is that with every biomedical instrument that you will ever make, something else creeps in, and that's the noise. And so this chicken example was maybe, I don't know, the clearest and not clearest way to illustrate that, okay? So now we need to talk a little bit about signal and noise. I'll do a big lesson in a small space. We have this notion that we are making devices, right? And the devices have a sensor, and on this end there is a display. Right? And here we have a circuit. And we define this thing called the measurand, which is simply the thing you want to measure. And that measurand exists out here, right? Measurand. This is the measurand. Let's call it the actual measurand. And it's so simple, right? What does a good device do? It shows you on the screen the value of the measurand. So if the measurand is temperature, the screen shows temperature, right? And it should be, of course, accurate. If the measurand is strain, like the strain on the chicken's leg, then a good device should on the display show strain. That's it. It doesn't matter how complicated a piece of equipment is, that's how they all work. You have a measurand and you have a display, and the display should reflect the measurand. And your ability to be a good biomedical engineer depends entirely on the fact that this is an accurate reading of this. Because if it's not, well, that's not good. I'm measuring my son's temperature, right? And if it's over a certain amount, I need to take him to the hospital. But your device shows me the wrong value, and I don't take him to the hospital. And that has consequences. You make a device that needs to detect the presence of a tumor. What is the consequence when your instrument fails to detect a tumor? What is the consequence when your instrument reports that there is a tumor where there isn't one? Yeah, you have a question? What's that?
I was just about to answer what you said.
Oh, yeah. So you know where I'm going, right? So that's our job here. So, okay, well, what could possibly go wrong, you would say? Right? What could possibly go wrong? Now, another term we can use for the thing we want to measure is the signal. Okay, that's the signal, right? Like I'm signaling you, you need to see it, right? What if your device instead or also measured something else? What do you mean something else? Well, I mean, for this example, this would be an example, right? You have a device, and it doesn't just measure strain, it also measures temperature, right? You gave me a thermometer. It doesn't just measure temperature, it's sensitive to air pressure, right? You made a cancer detector. It's not just sensitive to the presence of cancer or not, right? It's sensitive to also temperature, right? So some patient happened to come in and they were hot because they were stressed out about being tested for cancer, and your instrument indicated the presence of cancer when it was not there, right? What a horrible outcome. What a complete failure of the entire reason why you made this instrument. Now, can this happen? 100% of every instrument you will ever make will be sensitive to this. Some of you have made a very base, used this circuit, right? And you used a thermistor here, right? And you measured the voltage, right? Everyone did this, right? You made a battery, you made a resistor, and you put a thermistor right here and you measured the voltage, right? And you're still working, right? And this voltage here is supposed to track the temperature, right? It is a temperature measurement device, right? You know at this point that it would be a very bad idea to take the sensor and to start shaking it. You wouldn't do it, would you? Right? If you're trying to measure the temperature of something, you know, don't touch it, right? Because it turns out that instrument you made, if you shake it, something happens to the output. You made a device that is supposed to measure temperature, but it also measures motion. Something else. Now, in that case, you have a solution. You say, well, just don't move it, right? Don't shake it, right? But what if you couldn't? So understanding signal versus noise and dealing with it is what gives you, that $1 billion. And I don't mean $1 billion like in a, what's that word? Like in a hyperbolic way. I mean $1 billion, okay? Make a watch that measures blood glucose. $1 billion. The problem with that, the challenge there is not signal. The problem there is noise. And we're going to see that again and again. So we have to understand noise, because it's noise it's understanding signal to noise that makes you successful in projects, whether it's in this class or running a multi-billion dollar company. You have to understand noise, and it's always there, not sometimes saying, well, it's not always there. Does that make sense? Okay. So your device will measure something else, right? And again, here, I want to emphasize, why is it so bad? It's so bad because you don't know it did it. In this case, you didn't know that the chicken didn't just get heavier, right? You would conclude that when the temperature goes up in the room, strains on bones go up. That person me, the dad who made the measurement, and I read too low a value because you gave me something that's sensitive to air pressure, I don't know that it gave you, see, it's not that it's the wrong value. It doesn't say, oh, here's a value, but hey, it's wrong. You don't know. That person who was just told they have cancer because they were warm, they don't know that. You see why it's such a nasty consequence? They don't know that it was wrong. And you just told, and something else we talked about is that what happens after here is a decision. And if you want to be a good biomedical engineer, always realize that there's always a decision. Take my kid to the hospital or not. Cut out a portion of someone's body, or do not cut out a portion of their body, or put them on like chemotherapy. There are very serious decisions. And if your device cannot distinguish between signal and this other thing, and this other thing we will call noise. If your device cannot do that, not only do you not do very well in projects in this class, right? You end up producing devices with disastrous consequences. Okay. So signal to noise is a really big topic. But what I've realized is, like with everything else, it actually has a very, very simple explanation. Isn't that interesting? So whether you're getting an MRI, right, for cancer, or whether you're making a temperature probe, right, that isn't going to be sensitive to a kid moving around, right, or whatever, there's only one thing you need to realize. And the question is, well, why is there noise? Let's go to this bizarre example, but it proves the point. The noise happened because your sensor wasn't just sensitive to the signal, it was sensitive to the noise. And that's how noise gets into instruments, right? That's how a grandma gets the wrong diagnosis of cancer. That's how a kid doesn't get taken to the hospital when they should have been, or they get taken to the hospital when they shouldn't have been. It's right at the level of the sensor. It's not because your display isn't bright enough. It wasn't because you used a 9-volt battery instead of a 10-volt battery. No, that's not where the noise comes from. It's not because the packaging is red. It's not because it's sold at CVS or, no. It happens right here. Because the way I've drawn it here, right, it was a setup, right? Remember we said that what an instrument does is determined by the sensor. That's why I think this class, right, sometimes could be called sensors, right? If this instrument is a temperature sensor, it is because, temperature measuring instrument, it's because you have a temperature sensor. If this instrument is a strain gauge amplifier, that's what they call them, it's because this sensor is a strain gauge. If you have a device that is a blood glucose monitor, what makes it a blood glucose monitor is that the sensor is sensitive to glucose in the blood. It all happens here. The rest is voltage divider. How does the voltage divider? The voltage divider doesn't know. The voltage divider doesn't know if you want to measure cancer or temperature, right? Voltage divider does voltage division. It's all here. And so now we can see that the only place where noise can penetrate into your system, I mean, there are going to be some, of course, like everything, right? There's going to be variations, is at the level of the sensor. That's how the noise creeps in, right? Because the sensor that you used to measure the presence of cancer was also sensitive to temperature. Not the whole instrument, the sensor. All right? The sensor that you made for me to measure my kid's temperature, the sensor was also sensitive to pressure. You see how so it's like a super huge, it's a billion, it's a huge problem in biomedical instrumentation. In fact, it's all of biomedical instrumentation is dealing with signal to noise. But what I've realized is that it all shows up here. That's why in this example, it was very obvious for me that I could tell you this. You chose a sensor that was sensitive to strain and sensitive to temperature. And that's how the problem arose. This is such a major, major concept. Is this clear at a conceptual level? Right? So, when I showed you these circuits, I think if we don't talk about noise, it's not really clear why this is better. This worked. You have math. Can you solve this math? You can solve this math. This one here also works. Can you solve this math? You can solve this math, right? I want you to be aware that we're going to have a situation where, I'm going to do it right here, where as the strain goes up, R sub 1 will increase by delta R. R sub, no. Let's do the, sorry, R sub 2. R sub 3 will decrease by delta R. R sub 3 will decrease by some delta R. Oh, I nailed these wrong. R sub 4, or R sub 1. And R sub 4 will decrease by delta R. All right? When we set this up here, right, we had a situation where 2 of the resistors were going up with bending and 2 were going down, right? I added this here for a reason. It's going to come back in a second, right? But just conceptually, you understood that this was happening, right? Oh, hold on. Let's wait for the rattling. But this is just more complicated than this. Why do this? If you're just talking about signal, there's no reason to do this. Why you could have just had 1. Now you got to glue 4? Why do this? So, because when we do math in class, there's no noise. And so it's only because you realize that you have signal and noise does it really matter. Okay? All right. Now, a couple more things before we wrap this up conceptually. There was a portion of this class where you were making instruments that were supposed to measure temperature, right? In that case, what is your signal? Not a trick question. The signal was the temperature, right? I know, sometimes things are so simple, like even saying it makes it more complicated, right? But when you made instruments that measure temperature, well, the signal, the thing you wanted to measure in that case was temperature, right? Great. In the case of the chicken, when you made an instrument that was supposed to measure strain, the signal was strain. And what was the noise in this case? It was temperature. So wait, Professor, you just said the temperature was signal. Signal to noise are not things that are assigned like, like when God created the world, right? He said, here are the signals and here are the noises. No. It depends on what you want to do. So if you're working on a temperature measurement device, then for you, temperature is the signal. But if you're making a strain gauge measurement device, for you, temperature is the noise. All right? And so that's where we have to be so careful in how we define these things. This is the thing that you want to measure. This is the thing that you do not want to measure. All right, you want to get that door? Yeah? Okay. Does that make sense of how I defined it this way? And you can see how it's a bit tricky because if your goal, right, is to measure, is to create a watch that measures body temperature, then signal is temperature, right? if your goal is to make a watch that measures acceleration, and it shouldn't change depending on how warm the room is, now signal is noise. So you could have two people working at the same company, but for one person something is signal, and for the other person something is noise. And that's an interesting idea. So we need to keep that in mind as we juggle things. All right. So in this case of the chicken, we had a sensor that was sensitive to what was in this case the signal and what was in this case the noise. Okay. Now, how then do we get something that is not going to be sensitive to noise, right? And I'm going to set this up for you. Which of these quantities would be 0 to make it insensitive to temperature? All of them would work too, but you still want it sensitive to strain. The alpha. Because if we make alpha here, I'm going to do it right over this. If we make this 0, then it's gone. Why? Because philosophically we can see that the sensor is no longer sensitive to the noise. And if the sensor doesn't pick up the noise doesn't show up. We nipped it in the bud, right? Because this is the only place the noise can go in. Or if you want to say mathematically, by getting a temperature coefficient of resistivity of 0, the resistance, it doesn't matter what the temperature is, 1 degree or 1 billion degrees, it has no impact. Oh, okay, so can I just get one with 0? No, they don't exist. When you go shopping for strain gauges, right, it'll be, let's call it Model 1. Model 1. You will get a gauge factor. Now let's say that gauge factor is 15. And you will also be given its temperature coefficient of resistivity. Let's say it's 100. You could say, well, excuse me, I'm shopping for strain gauges. I don't know what this is. I don't care about it, right? Then you notice they sell another one. It's called the Model X. Its gauge factor is 5, and its temperature coefficient for temperature, right, this is for temperature, is 0.001. Now you say, well, look, I'm in the strain gauge business. This is 15, and this is 5. So I'm just going to do this one, right? I'm going to have more sensitivity, right? This is a bigger number, right? So when I have a change here, I'll get more of a change here. Of course, this is a setup because you're going to say, but hold on. Look at this. This Model X was made out of a material that is not sensitive to temperature. So even though I can't get this to 0, I can get it low. I want to again go to the high level. Will you ever in your career work at Strain Gauge Incorporated? I don't think so. Will you somehow in your life be measuring the strain of chickens? Email me, right? Dear professor, you're never going to believe it, and there's you with like the chicken with a wire coming out of it, right? No. But what is going to happen is that every single biomedical instrument that you ever work with will have a sensor. And every single biomedical instrument that you work with will have a sensor that is sensitive to both your signal and noise 1, noise 2, noise 3, and noise 4. And your ability to make a device that is superior to the ones that came before it, your ability to make a device that does not tell the person that they had cancer when they didn't, right? And does not send the child to the hospital at 2 a.m. when the child was simply moving around, depends entirely on your ability to get rid of the noise. If this wasn't a problem, we wouldn't have this class. I want to make it pretty clear here. There would be no class. There would be no why would we have a class on biomedical instrumentation? Just buy it. It's solved, right? Why would a company hire biomedical engineers to work in biomedical instrumentation? Why? So you can help them with their branding? Is that why you hire a biomedical engineer? so you can help them with their logo? No. So it is a fundamental problem. It is also the fundamental thing that you are being trained for in this class. Yes? So the question is, can we simply reduce the thing that contributes to the noise, right? And so let's go with how to reduce impact of noise. And we will come back to this list. How to reduce the impact, right? Number one, remove the noise. So for example, let's say you have a temperature measurement device that is sensitive to motion. Well, then hold it still, right? Get a, an air conditioner in the room so that the temperature doesn't change, right? This should be your first go-to. Like just remove, it's not always possible. I can't tell my son to stay still. But your point of, and I think your question was, if we remove it, do we remove the signal? Well, no. Like in this case, if our chicken coop now had air conditioning, well then we would remove the influence of temperature, but the strain would not be removed.
My question is more like in terms of the material components of the sensor itself, by changing the alpha.
Oh, but right, your question about the materials, correct. The difference between these are materials. So in this case, a material was chosen with a decent gauge factor, but this material here is very sensitive to temperature and this is not. So correct, we are trying to pick materials, right? In this example we're talking about, I would want a material which, this thing here, I deleted it. I wanted something where the resistivity does not change with temperature, right? Because remember, temperature doesn't really influence these other ones. So I would want something here where this is not sensitive to temperature, but it might be sensitive to stretching. I'm okay with that. I'm okay with if in the process of stretching it, I change its structure, right, in such a way that this is impacted. So it's not that this term can't change. I just don't want it to, yes. So step number 2 is always pick a good sensor. Not in some biomedical instruments. In every single biomedical instrument, one of the most critical decisions is which sensor you get. And it turns out it's not hard to find sensors that are sensitive to the things you want. Now, it's finding sensors that are not sensitive to the things that you don't want. Okay? It turns out that this and this are not enough. They're not going to be enough in the examples. They're not real in life. You could say, well, don't they just make one that does? No, they don't. So the third one is to think a little bit about how you design your circuit. All right? And I'm going to show you one example of that, of how you design your circuit. And it's already here because I always try to set things up that way in class, okay? So we just tee it all up, okay? You're back in the chicken lab.